Okay. Uh, Good morning, everybody. Today, I will do some exercise on some electromechanical equipment, basically the turbine and the penstock, the hydromechanical equipment penstock. And I will also use the uh, the Excel template for you to uh, do some exercise practice. And the Excel sheets, you have to enter some parameters. Then the output is automatic, as we did for some of the civil works components on Monday. And to start with, I would like to start with the, sorry, let me just, okay. So basically, the exercise will do today are focusing on two parts. One is the penstock, design of penstock, selection of the parameters for the penstock. And the other is basically selection of the turbines and calculating some basic parameters once we know the discharge and the head. Uh, as you know, I think I presented the previous lectures, I used the certain schematics to explain the.
Da gravidade da situação, era ou não.
So I basically use uh, the just give me a minute, please. There is some problem with my cursor. Okay, so basically, penstock is an important part of the hydropower project component because it basically conveys the water from the forebay to the powerhouse over here to the turbines, and uh, it the cost of the penstock can be a good portion of the total cost of the hydropower project, especially the projects on micro and mini hydro projects. And basically, the selection of the penstock, design of the penstock involves uh, different factors. The first one being the material we use for the penstock. Do you want to use normal the normal materials used are mild steel and high density polyethylene pipe, HDPE pipes. But nowadays, there are also using PVC, UPVC, and also what they call glass reinforced plastic, GRP. And the other design consideration we want to find out is what should be the diameter of the penstock. Okay? And this diameter is selected to make sure the head loss in the penstock is within an acceptable level. So because you see basically the gross head is the difference of elevation on top of the water level at the forebay and at the turbine level. So this is basically the gross head. But you have losses in the penstock. So you want to minimize those losses. And normally 5 to 10% loss is acceptable loss in the penstock. So, but the loss depends basically on the on the diameter of the penstock and the number of bends and contractions. Uh, there is friction loss and there is loss due to the bends, contractions, and expansions. And also, we want to make sure the thickness of the penstock is safe from the design head, because the water that flows in the penstock is under pressure. There is a pressure head. So in the beginning, the pressure, the potential head, the pressure head is the potential head is low. But when you come down at this level, as you move along the penstock, lower portion has high design head. There is also what is known as the surge effect. When there is when you shut down the turbine or when you open the turbine, then there is what is known as a surge. The water pressure, the surge increases up and down. So there is a positive surge and there's a negative surge, which creates pressure on the wall thickness of the pipes, of the penstock pipes. So we want to make sure the thickness pipe is able to manage this surge effect, which is also known as the water hammer. As you might have known that in your house water supply plumbing in the house also, when you open the tap, when you close the tap, there is a surge effect. So, and but in the case of hydropower, when the head difference is high, this surge effect can be substantial and it can put pressure on the thickness of the wall. Also, you want to make sure that the penstock can be both underground. This is underground, it's buried under the soil, but it can be overground also. When it is overground, you want to keep a minimum of 300 millimeter spacing clearance so that the maintenance and other activities is possible in the penstock. Similarly, if it is a buried underground penstock under the soil, you want to maintain at least a 1 meter of soil cover, especially for high density polythene pipes, so that it is not damaged. When there is a vertical load of some people walking or some load on the top of the soil, it does not impact the penstock pipe. And to select the alignment of the penstock, you have to first decide on the location of the forebay. So you have to find a good location of the forebay, and basically the location of the forebay is in such a way that the maximum head, you want to be the forebay as high as possible. You bring the water from the river as losing as little head as possible, and from here, from the forebay, you want to make sure that you get the maximum head up to the turbine. And practically, the ground slope should be 1 to 1 to 1 to 2, vertical 1, horizontal 1, or vertical 1, horizontal 2. And you try to minimize the number of bends, because when you have bends, you have to have anchor blocks, and you also have additional losses because of the bends. When the pipe bends, there is a loss in the head loss in the head. Especially, you want to make sure that the alignment is in such a way that you have the location of the powerhouse is, you have space for the powerhouse. So you have to decide on the location of the powerhouse, you have to decide on the forebay, then you have to find the best alignment along the slope of the hill or the topography to lay out the penstock. So powerhouse area has to be decided. It has to be on stable ground. If there is landslide or loose soil, the penstock can be damaged. The support piers may have problems. So this will then, when there is pressure on the thing, and if there is movement in the ground on the penstock, the penstock can break, so which will also create a problem. Other criteria is you may have a trail or a small walkway underneath. So you have to make sure that you cross such trails when you design your penstock. Okay. Now, the main criteria for the selection of the pipe is, as I mentioned, it's either mild steel or high density polyethylene pipe. And mild steel has diameter of less than 3 meters, and it has a length of 4 to 8 meters. High density polyethylene pipe are more what you call longer length, and also used for low head, because the wall thickness and the capacity of the pipe to withstand high head pressure is not as large as in a mild steel. So for very high head plants, at least in the lower section of the penstock, you have to have mild steel. Nowadays, there are rigid or unplasticized PVC and glass reinforcement plastics, which are also used. These are the materials. Now, what are the other factors that are important when you decide on the select the pipe is what is the flow required, what is the head and surge pressure, the durability, the allowable head loss, as I mentioned, and also because sometimes these mini and micro hydro projects are in remote areas. Sometimes you have to transport them, and you also want to make sure it is easy to fabricate. You have to join these penstock pipes because this has to be number of pieces. And of course, finally, the cost is important. And from here, you can see mild steel are heavy. It's got a specific gravity of 7.85, SDPI is 0.95, PVC 1.3, GRP 1.5. The compressive strength is, of course, the highest for mild steel, and the HDPI has the lowest one. GRP is a little less than mild steel. The tensile strength, of course, again, the mild steel has the highest, then followed by thing, and this is the Young's modulus of elasticity. Basically, the elasticity, of course, is the ductility sort of a thing, is highest for PVC, sorry, in fact, GRP, mild steel, and the lowest for SDPI. So these are certain conditions, and when you have a steel pipe and SDPI, the high density polyethylene pipe, you have to have certain connectors to couple these things, and this is basically a schematic of how it is coupled. They've got a loose flange and an end color, welded flange. This is on the right is the mild steel, on the left is the SDPI pipe. So these are basically construction related factors. And as I mentioned, the most important thing is basically the diameter of the pipe. And when you decide on the diameter, it basically you want to minimize the loss in the pipe. If you have large diameter, the loss is low. But again, the velocity is, if you have large diameter for the given discharge, the velocity will be low. So the cost will be higher. But if you have low, smaller diameter, the friction loss can be more. So you have to optimize the diameter. You have to make sure that the abrasion, the material of the pipes are able to withstand abrasion, and because there will be some sediment particle in the water that flows to the turbines. Although we will try to minimize these sediment particles through settling basins, but these sediment particles, especially when it flows under pressure on the high head, it can create abrasion. So the cost of the penstock is another factor. You want to optimize the cost, and also you want to make sure that the turbine cost and generator, the startup stopping conditions will get the surge that will generate. You want to make sure that this diameter is these pipes are able to handle that. And of course, in some locations, the type of pipe you want may not be available. So you have to also look at the local manufacturing capacity. And basically, when you design the penstock, you consider a velocity of 2.5 to 3.5 meter per second. And because if you have high velocity, you will have chances of high abrasion. But if you have low velocity, there will be chances of sediment and other deposits. So this is the optimal velocity you want to maintain. And what are the main head loss in the pipes? This is mainly due to the friction effect and due to the entrance and bends losses in the when you have the bend of the pipes, there are losses on the losses that will occur. So basically, when you want to select the pipe, these are the steps that you will use. And to calculate the velocity, basically velocity is discharge Q divided by the area. D is the diameter. Area is pi d squared divided by 4. So this 4 goes on the numerator. So it becomes 4Q pi d squared. So basically it is discharge divided by the area. And of course, area is dependent on the diameter. And D is the diameter in meter. The permissible velocity, basically, we said 2.5 to 3.5, but you can also, US Bureau of Reclamation has design guidelines, and they give this factor based on the head, what is the velocity that you want to is allowed. Sorry, I made a mistake. This is not rated discharge. This should be rated head, not discharge. Okay, so H is head, not discharge. So please, please correct this mistake. It should be rated head. And to calculate the head loss, basically there is an equation called Darcy-Weisbach equation, which is basically head loss is a function is equal to F is the friction factor, L is the length of the penstock, V is the velocity, 2GD, 2G is the acceleration due to gravity, and D is the diameter. And the fraction F, the friction factor F, depends on what is known as the roughness, pipe relative roughness, K divided by D. And K roughness value for different type of pipe material, smooth pipes, PVC, HDP, MDP, glass fiber is 0.06, concrete is 0.15, mild steel is 0.06 to 0.0, sorry, it should be 0.152. I think I will check. So it's basically 0.06 to, it's in between these two factors. And how do you calculate this F? Is basically F, there is Moody's is a chart, is a monogram we use to calculate the friction factor. Once you know Q and D, and once you know K by D, you can calculate the friction factor. And based on the friction factor, you can calculate the head loss. So these are just formula I want to just give it to you. And as I mentioned, the other losses are entrance, expansion, contraction losses. And the basic formula is V square over 2G is what is known as the velocity head, and K is the coefficient of expansion or contraction or entrance. For entrance loss, the coefficient K is, for sharp edges, it's 0.5, round entrance, it's 0.1, and bell mouth is 0.05. For sudden expansion, this is the formula. A1 is the incoming and A2 is the outgoing area. And sudden expansion, sudden contraction is half of this. So basically, this is the value of K. Similarly, for gradual expansion coefficient, then these are the values of K. And for gradual contraction loss coefficient. These are the value of K. So these are, and these K values are used with the velocity head. And for the bend losses, when you have a bend, this is the value for K. So these are for expansion and contraction bend losses. We calculate these losses. So based on all of these losses, you calculate the energy generation, the power loss. No? So once the diameter increases, the power loss, all the head losses will decrease, which means the loss in power is also decreasing. But also the other factor is, so once the diameter increases, the cost of installation increases. So now you want to find an optimal cost where the cost minus the loss is minimum. So which is equal to, based on the revenue of losses. So once you increase the diameter, the losses increases, the revenue and minus the installation cost will be here. But after certain diameter size, the cost is higher than the gain you have in revenue. So basically you come to a point, what is known as the optimal minimum cost point, total cost point for the diameter, and this is the diameter you select. Okay, so this is based on the optimization of loss. When the diameter increases, the loss decreases, but the cost increases. Also, you need to calculate the thickness of the pipe, calculating the stress in the pipe due to head and surge head. And so there are methods to do that. In the exercise, it's already given there. In the textbook, it's how to calculate the surge. All the formula are explained. And you add 2 to 3 millimeter to allow for corrosion. So in general, the total head loss for design flow is between 5 to 10%. If it is higher than 10%, you try to increase the diameter. If it is lower than 5%, you decrease the diameter, as it might not be optimal. These are thumb rules. But for detailed, large hydropowers, you carry out a penstock optimization exercise as shown here. And as I mentioned, the surge pressure in penstock is when there is an automatic closing of the valve and opening of valve. There is this positive and negative surge, which is due to sudden blockage of water, a rapid change in velocity, also known as a water hammer. You must have known about this in your house plumbing system also. You have the same situation. So you want to make sure that the surge, because this is the head here, the surge, the positive and negative surge is higher, the head thing, than the head over here. Because if you have the hydraulic head above this negative surge, then you can have a negative pressure on the penstock, which would have problems of stability. Okay, so when you do the penstock design work, these are the checklists that you follow. You have to decide on the penstock material, compare costs of all available in the market. You have to decide on the alignment, the practical ground slope. What is the practical ground slope? Where is the space for powerhouse? What is the best alignment to minimize the number of bends? For mild steel pipes, we have to decide on flange connection and site welding, specify appropriate coats of paints. For mild steel, because you have to look at the connecting from one pipe to the other. And you have to also, you could have some part of the penstock buried and some over the ground. So you have to compare the advantage and disadvantage of buried and above ground penstock. You have to make sure that the diameter is between, in such that the head loss is between 5 to 10%, as I mentioned earlier. You have to make allowance for surge effects while sizing the penstock wall thickness. The thickness should be able to withstand the water hammer, the surge pressure. And also you have to make sure the factor of safety is sufficient and the pipe's length and weights are such that it can be taken to the hydropower construction site. So these are the checklist when you design a penstock. Now I will just come to the exercise part of the penstock using the Excel sheet exercise 2 I shared earlier. So you could open that, and basically in the worksheet you will see that you basically initially find you give the design discharge, the design head, and the water level upstream and other thing, and then you also have the entrance, exit, and the bends. Then you calculate the head loss. So you get the percentage head loss. Then based on that, you select the material and thing. You also use a trash track. There are some parameters for trash track. Then the expansion joints have some parameters. Then based on these, you also calculate the head loss in trash track, the surface area, like we did. This trash track design is similar to the design we did for the intake. The side intake, we also designed the trash track. So we use the same method to design this. And basically, based on that, we check the total head loss, friction, and turbulence because of bends. Then we calculate the power of turbine and basically what will be the head loss up to the turbine, and to get that optimal optimal diameter where the total cost, the cost of the pipe minus the revenue loss is minimum. Then basically you do the dimensions of and the position of the plants. And just to give you in the example that I will show you in the Excel sheet, we are basically, there's one example of a given head of 180 meter, discharge of 450 liter per second. So we want to find the pipe thickness. This calculation is automatically done in the Excel sheet. But just to give you an example, if you consider a 4 millimeter thick, 300 millimeter diameter pipe, what is known as the calculate the wave velocity, and this is the head of the surge. So the one, that diagram I showed you earlier, that 51, this surge head is, so you have the total head is 180 meter, but you have a surge head about 51 meter. So this is how you calculate to get the pipe thickness, and based on the total gross head and the surge head, so you have to design the thickness of the pipe to withstand the head of 231 point some meter. And the thickness is equal to the formula to get the thickness, and based on that we get a value of 3.55 millimeter. So you need a 4 millimeter thick penstock pipe. The factor of safety, P effective, H total, comes to 2.79, which exceeds the allowable factor of safety of 2.5. Hence, this is okay. This factor of safety should be used for designing the inner penstock. So based on that, I will now quickly show you the run through the Excel file. Just give me a minute. Just give me a minute, please. Just give me a minute, please. I'm trying to open the. Yeah, okay. Yeah, can you see the Excel file now? Yes, I think you can see. So
Yes.
yeah.
Yes.
Yeah, this is the the blue one are the parameters that you have to input, and based on that you get the hydraulic calculation, the velocity, and other total pipe area and other thing are calculated automatically. And the factor of safety and other factors, the factor of safety is 2.79 as I showed here. The calculation I showed in the presentation PowerPoint, whereas the the outputs are now you can play with it in your free time. Please play with these Excel sheets, and you can see the different parameters and how these are calculated, like how the pipe area is calculated, hydraulic radius, velocity, roughness, Reynolds number, which is to get the Muller's, to use the Moody's thing, you need the chart, type of flow, it's turbulent, friction factor, you need to get the friction factor, which is based on the formula that I mentioned. And then you get the different factor of safety as I showed in the in the presentation. So this is the turbine efficiency. Then you get the power, electric power thing. So these are I think if you to go to the details, you'll have to see. And also you can you enter the discharge because it goes 450 liters, so 0.45. So in each pipe, we just have one pipe. Sometimes you can have two penstrokes. You can have two turbines and generators that can be directly supplied by two separate penstocks. Okay, so gross head is here. The type of and normally in micro hydro, they normally use Pelton or cross flow turbines. I will talk about these turbines later. And as you know, Francis turbines, as I think in lecture 3, Hydro03, we did the comparison of penstock, of Pelton, impulse, and reaction turbines. So sometimes the Francis turbine are difficult to fabricate and maintain. It's very sensitive. It's a reaction turbine, whereas the cross flows and Pelton are easy. So, but of course, I will later today, in the second half of this lecture, I will talk about the cross flow and the Pelton, the selection of the turbines. So number of jets, how many jets you want to use, because you can have multiple jets of for the Pelton. So is it a direct coupling, closing time? These are standard documents. What is the water level of the forebay? What is the percentage head loss here, cumulative known efficiency, and you also, because you want to get the economic. So it's basically, I think this is whatever I presented in the presentation is shown here. And okay, so in the presentation, I calculated the surge and the thickness. This is already calculated in the Excel sheet. So I would like you to, I will not go into the detail of each one of these, but if you follow this and if you follow the main parameters I have described in the lecture notes. So this is just to give you an example of how a penstock is designed and how the the factor of safety of the penstock are calculated. So with that, I would like to stop for some questions. If you have any questions on the design of penstock, I will be very happy to answer. As I mentioned, some of the formula, I mean, if it is, because if it is not clear from here, there are standard textbooks and the manuals I refer in the references. If you Google, you can get these manuals in the internet also. So if you want, I will also, I can put it in the Dropbox also for you to download, especially the micro hydro design manual and these where these Excel sheets are also explained in a better way. Okay, so can I, is there any questions or comments on the design of penstock and how the pattern?
Yeah, good morning. I have a question. I saw the penstock, those long penstocks, they don't take any valves and hydraulic. How do you deal with hydraulic hammer?
Yes.
And when you do maintenance to the turbine, how do you control for that?
Yeah, thank you. I think that's a very good question. Let me just go to that PowerPoint. Okay, yeah. You see, like this one, this is the, when you, actually, like I mentioned, if you have, I mean, over here, there's a valve here. No? This valve will lead you to the turbine. So now sometimes you have to close this valve here. Okay. Actually, you can have a gate on the top here. Hello. Yeah. Sorry. On the top also you have a gate, so you close the gate. If you close the gate, all of a sudden, as you mentioned, there is a turbine generator working here. So it will, all the water will, there will be a water hammer effect. And also when you close the valve here, there is also, again, when you open and close, there is a water hammer effect. And this water hammer effect is the negative and the positive surge. No? Sometimes when you automatically close, what really happens? There is a surge in head. So in fact, the pressure that builds up here, over here, is like up to, like here, over here, the total pressure is from here, sorry, the head is from here to this here. So the turbine has to be designed, the wall thickness, sorry, not the turbine, wall thickness of the penstock has to be designed so that it is able to withstand not just the hydrostatic head of hydropower, but this additional head due to a positive surge. So, and this is basically the water hammer effect. In terms of negative surge, what really means is that over here, in this portion here, the hydraulic head is from here to here. Okay, the hydrostatic head is from here. But whereas there is the negative surge is below the hydrostatic head. So in this portion of the penstock, there is a negative pressure on the penstock. Okay? So this also you should try to avoid. When you have a negative pressure, then the penstock will sort of almost like a collapsing situation over here, because it is the atmospheric pressure. The pressure outside is more than the pressure inside. So you have the stress. It's a compressive stress on this penstock. So when you design this penstock, you try to make sure that the alignment of this of the penstock is in such a way that you don't create a negative pressure on the penstock, number one. The other thing is you design the penstock diameter from here to manage not just the normal head, the hydrostatic head from here to here, but also considering the positive surge. So with that, you can, once the penstock is designed, the wall thickness of the penstock can withstand this positive surge, then there is no problem to shut down the, to close this valve and stop generation, stop the flow of water into the turbines. So this is part of the penstock design methodology. Yes, Mr. Kamal, did I answer your question?
Yes, thank you.
So much. Yeah, any more question? Otherwise, let me just let me start the, maybe today I want to a little bit, because I have a lot of material, I want to go a little fast, not fast, but I want to cover a little more because I want to also give some time for the exercise. Okay, so this was, I mean, of course, the Excel sheets are with you. You can practice in the Excel sheets. And actually today will be the last lecture for December, but we will meet after about 1 month. So you can practice the Excel sheets I gave you on Sunday on the civil works. That was Excel sheet number 1. I just divide the Excel civil work. And this is, today is Excel sheet exercise 2, where I divide the, I mean, we have the penstock and the turbine selection. There is some electrical components, some load and benefit estimation, which I will go over it also. And maybe if you, I mean, you can practice during this in December after this class. Then when we start our class next in January, you can ask me more questions if you have. Okay. So now, before I go into the turbine selection part, I just want to mention that you have to design the powerhouse also. And the powerhouse design has to make sure that there is enough space to house the turbine, the generator, and other components and accessories that is included, the inlet valve, the sort of the penstock inlet valve. There is a turbine, there's one turbine here, the generator, this is the penstock, the anchor block. So, but sometimes you can have more than one turbines, no? Especially for mini hydro, micro hydro, maybe you have 1 or 2, maximum 3 turbines. But for large hydros, medium hydros, you can have 5, 6, 7 turbines also. You also need to, the governor controls the flow into the turbines, as I explained, I think, in the previous lectures. Then you also need what is known as the controller, electronic load controller. Should also be, you have enough space for that. So you make sure that the dimension of the powerhouse is such that these turbine generators and other components and accessories are easily they fit into the space provided. And there are standard dimensions for this which you can follow. As I mentioned, the typical powerhouse is of this type. I think I already showed you this diagram. And the arrangement of the powerhouse, the layout of the powerhouse can be, as I said, you can have 3 different penstock, and then you can have 3 turbines and generators and 1 control panel, which will sort of, and from here, this is the tail race. Okay, so here is the penstock, then from the penstock, the tail race comes. This is what is known as the linear layout of powerhouse. Then you have a multi-layer. We have 2 units where the turbine and generator are in different layers. So this is more of a horizontal layout. This is a vertical layout, okay, of 2 units. You can have a circular layout. You have the penstock from this water. Then you have unit 1, unit 2, unit 3, unit 4, unit 5. So these are different arrangements of the turbines and generators and the accessories. And based on that, you have to decide on the dimension of the turbines. So this is, I think I will not go into the details of the turbine dimension, but now I would like to move to the important part of any hydropower design. That is basically the civil works is important, the headrest, the weir, the intake, the settling basin, the gravel trap, the headrest canal, headrest pipe, forebay, penstock are important. But finally, you also need the potential kinetic energy has to be now converted into mechanical and electrical energy, which is done through the hydraulic turbines. And these hydraulic turbines are basically, I just repeat a little bit of the theory that I think I provided earlier, but based on the basic hydropower system, as I mentioned, so you have this is the canal, this is the forebay, this is the penstock, then you have the turbine. And over here, basically, if it is a Pelton turbine, you have the penstock, then you have a nozzle, okay? You try to, from this diameter, you try to reduce the diameter of the nozzle so there is a high pressure flow, a high velocity flow that hits the turbine, that goes into the impulse turbine or a reaction turbine. And basically, the total head is the gross head, and the losses in the penstock is the net head. So this is the hydraulic head, H net is the hydraulic head. Then after that, you have the turbine efficiency and generator efficiency before you calculate the total power. So now, this is a very famous equation called Bernoulli's equation, which is based on the conservation of energy. And it basically says that the pressure energy, the kinetic energy, and potential energy is constant at two different locations. For example, so if you try to compare the location 0 here on the top of the water level of the forebay is 0, and this on the turbine level is level 1. Okay, so now the total pressure at this level is P0 divided by rho g plus P0 divided by gamma or rho g plus V0 square over 2z. This is the velocity head, the kinetic energy, and this is the potential energy head, Z0. Z0 is the top of this, from this location to the top of this location from a certain datum. Okay, and now at this at the turbine level 1, the pressure is pressure energy is P divided by gamma or rho 0 plus V1, so it should be 1, not A, V1 square over 2z. This is the velocity head, kinetic energy, and the potential head is the Z1. Z1 is the level of that thing, and the loss, penstock loss is H loss. Okay, so based on that, we know that P0 is 0 because on top of this, the atmospheric pressure exists. So that is equal to 0. V0 is because the water is cancelled. At this location, the water is at the same level. So velocity is 0. So based on P1 is the pressure head that at the inlet of the nozzle is the P1 is the pressure head here. V1 is the velocity in the penstock pipe right before the nozzle. Z0 and Z1 are height of water surface in the forebay. So basically Z0 minus Z1, Z0 minus Z1 is the gross, which is the gross head. So based on and H loss is the hydraulic frictional loss, head loss in the penstock. So H gross minus H loss is equal to H net. No? This, I think these are standard thing. And based on that, based on equation 1 and equating P0 is 0, V0 is 0, you get this equation. And similarly, you can also get the pressure equation for 1 is here and 2 is at the turbine here. Over here also, this is 2 is at the turbine and 1 is in the nozzle here. So you can get basically the difference. You can also get the energy here. And based on that, what you get here is, okay, so P2 is 0 because 2 is in atmospheric pressure. Basically, what you get here is V2 is root under 2G H net. So assuming, so what it means is assuming that there is negligible loss in the nozzle, all the potential energy other than the losses in the penstock is transferred into the kinetic energy as the water comes out of the nozzle. So basic principle is all that potential energy from water falling from here to here, except for the losses in the penstock, is now transferred through this nozzle, assuming there is the losses in the nozzle is negligible, is transferred in the kinetic energy. And this energy is equal to V2 squared over 20 is the H net. So this is basically the potential energy converted into kinetic energy. And that kinetic energy is then converted to mechanical energy and electrical energy using the turbines. And as I sort of presented in Hydro03 lecture about almost 2 or 3 weeks ago, the hydraulic turbines are of different types. You know? There are 2 types, main types, impulse and reaction. You know? Velocity turbine, which are Pelton, turbo turbine, reaction or pressure turbine. Nowadays, they have a new type of turbine called bulb turbine also, but these are new turbines that you can also see. So basically, now you have the Pelton turbine, and you have the impulse turbine, the velocity turbine, and you have the pressure turbine. Over here, just all the potential energy from the nozzle just hits the buckets, the runners, then rotates the runners, hits the bucket, rotates the runners, and converts potential kinetic energy into mechanical energy. Whereas in the case of reaction pressure turbine, both kinetic and part of the potential energy is also here, because this is under pressure. Okay, the casing is under pressure, and so this is one classification which I already talked about. And another classification of hydraulic turbine is they do it according to the direction of flow, which I presented already over here. I'm just repeating this slide from our previous slide. There is this tangential flow turbines over here, like Pelton is this. Okay, and so as I was mentioning, this is just a review. So hydraulic turbines are also categorized based on the direction of flow, and there are different types: tangential, radial, axial parallel flow turbine, Pelton Wilton, and mixed flow turbine, which are the Francis mixed flow turbines. And basically, nowadays, I did not introduce you that in the previous lecture, but I would also like to just briefly mention that there are very low head and river current turbines that are now in practice. One example is the Archimedes screw turbine, where it basically uses the velocity of the water current to develop, to generate power. and these are like it's less than 3.2 meter head. It's environmentally attractive because it does not require a dam, and also it also has minimum impact on the fish. And sometimes, especially in the developed countries, high-end plants are already developed, and there's also in the developing countries there are environmental opposition. So basically, these very low turbines, bulb turbines, split turbines are for very small head. But one thing you have to be careful is the efficiency of converting just the flow, kinetic energy in the flow would require very big turbines, like runners, like in a wind turbine. So it is the feasibility of such for large hydro is very limited. Okay, but I just wanted to mention that. Also, I also want to mention that nowadays the pump storage is coming into importance, and then we use what is known as the reversible pump turbines, usually a Francis turbine, which operate as a turbine as well as a pump. So it can be used to pump from a low reservoir to a higher reservoir also. So these are, so this is also another turbine that we need to consider. Just give me a minute. I just want to just 1 minute. I just want to check something. Okay. So these are the reversible pump turbines for pump storage projects also there. Also, this is just a repetition of the previous lecture, Hydro 3, but I wanted to mention this here because when we select the turbines, we should know that the differences between the impulse and the reaction turbines basically all is converted into through the efficient nozzle, whereas it's transferred to reaction turbine. Both pressure and kinetic energy is transferred, and these are the different differences. And one thing you have to understand is maintenance, repair of impulse turbine is easier compared to the reaction turbines. So these are some of the factors. And the main thing for selection of turbines was we know that is the head and the flow, discharge and flow. So for low head, as I showed, the Archimedes screw turbines are thing. The cross flow turbines are also within the range of 10, 20 meter head. Then you have the Kaplan turbine within range within 50. Then the Francis, the red one, from as low as 10 to 300 meter. For of course the high head, low discharge is basically Pelton. Then you have the turbo turbine, which also sort of overlap with Francis over here. So basically for small micro hydro, cross flow, turbo, and Pelton turbines are mostly used because Francis and Kaplan are expensive and difficult to manufacture also. Another factor here is, as I mentioned earlier, that for very river current and very low head turbines has a range of less than 5 meter head, very low head. Kaplan for low and medium. And there's a cross flow Banque Michel, what is known as low and medium. Francis low, medium, and high. Turbo medium. Pelton medium, high, and very high. So 50 to 200. These are basically the range, okay, in general. And for mini hydro, less than 1 megawatt or 500 megawatt, these are the different conditions here. But basically, we use, as I mentioned, cross flow, turbo, and other things. So this Osbaker turbine chart, this gives you the head and water flow and the chart, because I specifically mentioned the Osberger turbine because this is the turbine, German turbine that the Majau hydropower project in Mozambique is now just been using, and they're using the cross-flow Osberger turbine, which have been there for over 90 years. They are a very reputed company as far as I know. Okay, so basically, the other factor you have to understand when you do the selection of the turbine is the range of discharge, rated discharge. Basically the fixed propeller type, once the rated discharge reduces by 80%, there is a drastic drop in the efficiency. So when with 50% of the rated discharge, the efficiency drops to 0. With a 70%, it comes to about 60%. So it operates in a very narrow range of discharge capacity compared to Pelton and the Kaplan, and even Francis has that problem. So, and cross flow also, it operates up to about 60% of the rated discharge. It operates within the range of, it's about 80 to 83, 84% efficiency. So this is an important factor. So if there's a high variation in the flow, then we have to be careful how we select the, so basically the thing. So a fixed propeller would not be appropriate for that one. So similarly, one factor which is apart from the head and the discharge, the other factor that is needed that defines the selection of the turbine is what is known as the specific speed. And specific speed is basically defined as the optimal speed of a particular type of turbine with a capacity of 1 metric horsepower at a head of 1 meter. And this is the formula used. N is the NS is the specific speed, N is the operating RPM, and P is the power, H is the net head. Okay, so basically this is, and P is given in metric horsepower. If you use kilowatt, then we multiply by 1.1666. So basically, NS is the specific speed range for Pelton. It's 10 to 50, Turgo 20 to 70. So a higher, lower specific speed is for high head, low discharge, and higher specific speed is for high discharge, low head power plants. So head, discharge, and the specific speed are the three factors that defines that are used to select the turbines. The other speed is the synchronous speed. Is when you connect directly to the turbine, there has to be a synchronous speed, which means that the turbine speed has to synchronize with the generator speed. So based on that, you calculate the synchronous speed. So this is another parameter used for selection of thing. And the other one is the runaway speed. Runaway speed is the external load on the machine drops to 0, the governing mechanism fails. At the same time, the turbine tends to race up to the maximum possible speed known as a runaway speed. And a runaway speed should not exceed, and this is a factor based on the turbine type and the manufacturer. And there is another factor, what is known as the speed factor, is the ratio of the peripheral speed of the buckets or vanes of the nominal diameter D to the theoretical velocity of water under the effective head H acting on the turbine. So based on the phi speed factor, the type of runners are also given. So basically, what we want to do is we select the turbine based on head, discharge, and the specific speed. Just to give you an example, I will just show you one example of what type of turbine should we select. So which turbine type would be most suitable for a 50 kilowatt power project for which the net head is 40 meter and must drive a generator at 1500 RPM. The speed of the generator is 1500 RPM according to the design of the generator. Now we calculate the NS, specific speed, and so because we want to the turbine RPM and the generator RPM, we want to combine with a direct coupling, so the speed has to be equal. Now, based on this speed, we see that that it is 122, which comes to the Francis turbine category. 80 to 400 is Francis turbine. Okay. Okay, 80 to 400 is Francis turbine, and our calculation shows that the specific speed for 50 kilowatt, head 40 meter, RPM 1500 is 122. But as I mentioned, for micro hydro project, mini hydro projects, Francis turbines are not preferred because it is relatively sophisticated design and casting, and it may not be available in some less developed markets where cross-flow turbines might be locally manufactured. Hence, what we do is we try to also see that we will reduce the RPM to 750 RPM, which gives you an NS value of 61.5, which is within the range of the cross-flow turbine. So what you would do now is we use a belt and pulley system or a gearbox to double the RPM to drive the generator at the required speed of 1500. The turbine speed will be 750, giving an NS specific speed of 61.5 so that we can select a cross-flow turbine. So this type of decision is made for hydropower design. For large hydro, basically you will get you will go for the best design. Another option would be to also divide, instead of having one unit of 50 kilowatt, we try to have 2 units of 25 kilowatt, which will give you an NS value of 87, slightly higher than the range of the cross-flow turbine. But this could be checked with the local manufacturer if they can manufacture a cross-flow turbine with a specific speed of 87. In this case, we will need 2 generators, so we have to look at the overall cost also. So again, we could also change the RPM to 600 RPM, giving the NS value to 49, which is in the range of multi-jet Pelton turbines of 12 to 15. Hence, what we are saying is for a given power capacity, for a given discharge, we want to, there are various options of selecting, designing the speed of the turbines and the specific speed so that we can select a turbine type which is cost effective and available in the market. And for, as I mentioned, for mini and micro hydro, this is important because cross-flow turbines can be locally manufactured and are also highly used instead of Francis turbines. Okay? So this is just an example I wanted to give. You can look at it. Another thing we have to think is, I think I already discussed this in the presentation on Hydro03. There are 2 types of generators, synchronous and asynchronous. I will not go again, but I would like to mention that the turbines have to connect it to the generators to generate the electricity. Again, there is the governor mechanism which will help to regulate the flow to keep the speed of the turbines constant, because you don't want to have a load according to the load condition. We want to keep the turbine speed so that the frequency is maintained. This is required to directly couple to an electric generator to run at a constant speed. So that will be very nice. So 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 we need a governor. So basically, for a Pelton turbine, it increases the outlet area of a nozzle, so that the flow is controlled. For Francis and thing, it increases the wicket gate to control the flow. And another thing is, for reaction turbine, we need what is known as the draft tube, because the pressure reaction turbines have negative pressure at the outlet, so that we use draft tubes so that we can use the full head of the power plant here. So this is a draft tube, and there is a design of draft tube is also a factor, but these are available in textbook and other material. So now I would like to now briefly walk you through the template, the turbine selection exercise template that we use, which is the second sheet in the Excel file I shared with you today. This is the sheet on, okay, just a moment. So this is the turbine. It's a very simple thing. It's a simple, because we just want to check the what do you call, the specific speed, and we want to make sure that what would be the selection of the turbines. No? So this is an example. I will also do some calculation, show you some calculations first. Okay, so basically for micro hydro, mini hydro, we want to either use a Pelton or a cross flow turbine is preferred, as I mentioned. Okay, and as you know, the Pelton has a this is the maximum RPM, 400 to 1500. Efficiency is very low, is here, and this is the NS speed. Okay, the specific speed. So single jet 30 to 40, double jet 30 to 40, 3Z 40 to 50, cross flow 20 to 80. So what we do is we basically calculate the specific speed, and to reduce the what do you call, if it does not fall, the NS speed is not within this range, then we use a gear system so that we can change the speed, we can reduce the speed to our range, no, as I showed earlier in the exercise. So based on that, I would like you to, okay, here is the example. So this is, we have a discharge of, let's say, 150 liter per second, okay, and you have, maybe I should have put it in here, and okay, so this is, because since it is a micro hydro, so they have put discharge in liter per second, the gross head of 69, hydraulic losses, maximum turbine output, turbine RPM, gear to ratio, turbine ratio, number of turbines, number of jets in a thing. So based on that, so this is the net head we have, the hydraulic losses. So without a gear, we get a specific speed. No? This is the specific speed of 46. If you use, reduce that to 2, you get 23 with the without a gear. So based on this, we can either use a turbo or a cross flow, or Pelton or a cross flow. Okay, so because I showed you that the Pelton has a range from 10 to 50 based on on single jet, double jet, or 3Z. Cross flow is 20 to 30. So we can do we select the turbine based on that. So this is a very simple exercise which will help you do some analysis of the selection of the turbine. And for micro hydro, we try to select either turbo, Pelton, or cross flow turbine. It's easy to manufacture, as well as it is easy to maintain also. So this is very, in a simple way, this is the turbine selection procedure we use based on the specific speed. Of course, there are other criteria that are inbuilt, but this is basically the factor. So maybe I'll just stop here for a few moments and take some questions or comments you may have on how turbines are selected. Yes, please. Hello, do we have any questions?
Alguma pergunta, colegas? I don't think so.
No problem. If there are no questions, I would just like to move on and explain basically what I have in plan was I wanted to, I did not provide the details on electrical equipment, the transmission lines, and the load and benefits, but I would just like to give you a brief introduction to this exercise in the templates that I shared today, because these are, I think you have, I mean, you have some background on this, as well as you can, if you follow these templates, you can calculate the different electrical and transmission systems. Okay, so basically, again, over here, these are the different parameters you put, the overall plant efficiency, the discharge, the gross head, and the generator information. Then based on that, it gives you the capacity of the generator, the electric load control, correction factors are there given. It gives you the ballast capacity and other rated current, the rated voltage and other things. So this is basically for the electrical generator system, these are the key factors, okay? Honestly, I mean, I have some background on this, but I am more of a civil engineer. So I basically deal in the civil works up to the turbine as a hydropower engineer. But as far as electrical systems are concerned, then you have specialized electrical engineers who look at this, plus manufacturers. Also, once you give the rated capacity and the generation discharge and pattern, they will come up with the type of generator thing also. But if you look at the comments here, it gives you the equations that are used in micro hydro projects to get the voltage, the rating of the MCCB, the ELC capacity, and other factors. Okay, so you have, this is the generator capacity, because based on the efficiency and the head, it's about 26.81, 26.41 kVA, you know, which is about, we multiply this by, I think you need to multiply this from an active power of 12.83, then you get this kVA factor and other things. So this is one Excel sheet that I would like you to play around. Then the next one is, now you have to design the transmission and distribution system. Okay, so from the, because the electrical output from here is at the rated discharge of 400 volts, but you have to sort of supply the power to the customers in 220, 230 volt. So you have to have a step down transformers, and these are the branches. So you give this sort of a length of these transmission line, distribution line, the phases and other thing. And then these parameters are already calculated. I think Professor Paul provided a separate lecture on electrical systems, which also was covered there. And this system, this transmission distribution, would be common for other mini grids or power grids, including solar, photovoltaic, or bioenergy sort of thing. So, but as a complete hydropower to supply to the consumers and the end users, you have to design the transmission systems also. So there are certain ways, and basically once you give this kilometer, the phase, the nodes, the other parameters are automatically calculated. And it in fact also gives you the cost of the thing based on certain rates of the cost also. So these rate analysis is important. I will not go into the cost. This is just a practice thing for now, but we can have a look at it. So the electrical system, transmission system, also the templates are there. And also I would like to quickly explain to you the loads. How do you calculate the demand? Okay, like in my presentation earlier, I showed you this load curve for an isolated system. This load curve was arrived based on certain parameters. For example, so if you are doing a feasibility study or a planning study, feasibility study for a mini hydro, micro hydro project, you have to go to this system, the beneficiaries, and identify the location, the number of households, and how many days you want to operate the plant, and other factors. So for domestic light, what is the average subscription? What are the system losses? What are the timing for thing? Okay, so basically it gives you the time from 5 o'clock to 8 o'clock, and from 6 o'clock to 8 o'clock. These are the main lighting requirements. Okay, and these are the loads are calculated accordingly. Similarly, you have what are the domestic thing, what are the agro processing. I think this is okay, this is a little bit small. So this is the kilowatt hour load estimation. And so basically in this thing, there is an agro processing, bakery, there's a sawmill, there's herbs processing, and other type of thing. And so as I mentioned earlier, this is the current demand, the load. But in the future, once you have a micro mini hydro in that place, the demand there could be small enterprises, small business that will come up. And we say that it will take about 2 to 3 years after the installation of the micro hydropower project for these different business to come. And what is the tariff to be used, the metal workshop, daily processing, dairy processing, cold storage, and other things. What is the timing of these hours are given here. And so these are the operating hours. Then based on that, you calculate the total kilowatt hour now, the total then based on the supply and demand. So you get the basically load curve. Of course, you can play with it and get the graphs like this. So this is just an example that I wanted to show, but this is the demand assessment, the need assessment in the hydropower projects study. Okay, so basically, I think today this was, I think went a little fast with you. This was basically the 5 exercises that I wanted to present. The first one was the penstock. Second one was the turbine selection, and the electrical transmission and loads benefits. I want you to practice. And when we come back in January, if you have any questions, or you can write to me by email, I can provide you these answers. And basically, when we are doing evaluation, we'll also do in January and February, we have plans to do some evaluation. How do you evaluate? I think Mr. Kemal or some gentleman was asking me last time that what are the important factors for a feasibility study of a mini micro hydro project. So as I mentioned, the hydrological, the power generation are important. Then you have to get the cost, because cost of the civil works, the electromechanical works. So you have to have some basic design of these parameters. Then you have to do a cost benefit analysis also. So in January, we have one session where I will specifically talk about the cost benefit analysis of a mini hydro project. With that, I would like to stop now for a while. And if there are questions, comments, suggestions, I'll be happy to take them.
May I ask you a question, please?
Yes, please.
Yes, it is in connection of cost. Do you have a range of cost that can be acceptable, say per kilowatt or whatever, in order we get one ratio to evaluate the minor hydropower?
Yes, that is actually very important. And normally, I think the cost, like if you remember in one of in the previous presentation, I provided you the range of cost, and it goes even up to $5,000, $6,000 per kilowatt. But in some it is 2,000, 3,000. But normally, if you can bring, I mean, I don't know the cost in Mozambique. We have to see. It depends on the tariff also. But I would say a micro hydro project with a cost to 3,000, 4,000 per kilowatt would be economically. I mean, of course, I don't know. Maybe when we do the cost benefit analysis based on the tariff, we'll be a little clear on this. But I would say if the costs exceed more than 3,500 to 4,000 per kilowatt, it might be a bit costly. And of course, this is for when I say this, this is for more or less a plant with running at full capacity throughout the year. You know, because sometimes you can have a plant with only 60%, 70% capacity factor. When I talk about this, I'm talking about a capacity factor of a plant factor of almost 90, 95. So the best thing would be, I don't know, I think bringing it down to less than 3,000 might be preferred, but I think even something more could be feasible. But again, it is very difficult to, it will depend on the tariff and the location of these. And as I mentioned, there are subsidies, you know, like I said, even in my country, in Nepal and other Asian countries, the government provides subsidy to these hydropower projects. But if I may, let me just show you one. Okay, just give me 1 minute. I think I want to show you the range. Just a moment. Just give me a minute, please.
While you are finding the table, may you also talk a little bit about the payback period, set about payback period as well?
Yes, yes. But one thing you have to be, this is like, again, I think we have to maybe discuss this further, because the payback period, like I said, 10 years, 15 years is considered a good payback period. But also it depends on the discount rate, no? And this is a big economic, maybe I think we'll cover, BART has planned to have a special session on tariff or a request for. I will also contribute, but the discount rate, the payback period is very important. Yes, you're right. But I think coming to the cost, no, if you remember, I just like want to, I think it's important we see that. Just give me a minute. Just give me a minute. Yeah. Okay. Now, if you see, this is for large hydro. Okay. Now, okay, in like I'm looking at Africa, and you see that. Okay. So the average is little more than $2,000 per kilowatt. Okay. Sorry, I want to put a better pointer. Okay. You see, this is Africa. For Africa, the average is little more than 2,000 for large hydro. Okay. This is for large hydro. But if you see, China is now making for almost 1,000, 1,200 average. But sometimes even in China, there is up to 3,000. But there are some smaller projects almost around 4,000 also. In Asia, the range is very high. Okay? But this is for small hydro, sorry, large hydro. But for small hydro, okay, you are coming to around 3,000, 4,000. So I said, that's why I said about 3,000 here, maybe 3,000, 3,500 is the average. So because the cost of and the micro hydro would also be in this range. So this is the current range of cost based on the arena. But in Brazil, it's lower. Central America is lower. Europe is even higher. You see, because I mean, obviously they have higher costs and their quality. Asia is lower. The average cost in Asia, but there is a big range of cost in Asia. China also the average. This is I don't know if this is the average cost or the median cost. I have to check the thing. But anyway, but the average is around average or median. I think it's probably an average cost is even less than even for small hydro. So I think this is the range of at least that should be probably below 3,000, 3,500 or less, because the maximum is around 4,000 for small hydro. So I'm considering this in the range of mini and micro hydro. But you are right that we have to look at and even I will cover a little bit. I did not put that template now. I will cover in January. I also have a template to do a cost benefit analysis, okay, based on the tariff. But as I mentioned, because this costs $3,000, $4,000 cost for a rural area household, and the tariff based on that might be expensive. So the government provides special subsidy to bear the capital cost. At least the operation maintenance and the other, some part of the capital cost has to be recovered from the tariff, but part of it is subsidized also, especially for micro hydro, considering the economic benefit to the rural economy due to access to energy.
Thank you very much.
Yeah, thank you so much. Yeah, but we will discuss this in January. I mean, this will be because now the lectures now has been more on giving you the theory, the formula, the process. But I think in January and February, we will have to do how to evaluate projects, how to compare projects, because we have to also, I don't know, portfolio. You have to compare a solar, bioenergy, hydro. So what is the advantage? I mean, because if you have the option of a solar, PV, hydro, micro hydro, and a bioenergy, so maybe a hybrid is needed. So I think we have to compare in terms of cost. And as you know, I think you see this is the in terms of the levelized cost of electricity. So the unit cost is around 6 or 7 cents. Okay. Okay. I don't know the tariff in. I would assume the tariff is higher in Mozambique, but this is this in Africa for large hydro. But for small hydro, the levelized cost is per unit cost. This is the actual cost. So it is more than 10. The average median is more than 10 cents. So, and there is some losses, there is some overhead. So maybe the tariff would be, I don't know, 15 cents per kilowatt hour and other things. Now, it's always good to compare with China because they are very competitive now. In China, you see the average cost, levelized cost of hydro is about 2.5 to 3 cents, quite cheap. Even the maximum is lower than the average cost in Africa. So similarly in other Asia also. So in some ways, in Africa, the levelized cost of electricity from hydro and small hydro is almost at par with Eurasia and even a little lower than Europe. Europe is, as you know, because of the cost, the standards are high, maybe the cost of labor and the cost of other environmental and other requirements is also high. You see, and this is the fossil fuel range. You know, so so anything above is so. But still, what I mean to say is, it will be cheaper than diesel plant. Okay, so it will be cheaper than diesel plant. The diesel plant has a higher range. Yeah. Any more questions, comments? Dr. Carlos, if not, maybe I will stop here and
Yes.
and of course, as I said, we'll catch up in January. Today is I think for our we'll take a break after today, but
Right.
I look forward to again coming back and discussing further, and maybe we'll have, I think in the next few sessions after we return, we'll talk about the economics also, some examples of this cost, calculating this least cost, levelized cost of energy, the cost of capital cost, and you see now over here, the capital cost according to the project size is now this is overall, per kilowatt, it's around 1700, but this is an average. So I'm considering for micro hydro, it will be almost 1.5 to 2 times of this. So this is, yeah. I think that's, I would, if you don't have any questions, let's stop here and see you, have a nice weekend and see you in January.
Yeah. Thank you much, Divas. Let's
Yes,
see if there is any question. Alguma pergunta, colegas? Okay, I just have some recommendations for the participants. I just sent an email. I also sent a message on the chat alerting you that there is an email with the training evaluation form. It is exactly the same you have filled before, but now you'll do it by digital. But just download the Word file, fill in, and then send it, please, before 1 o'clock today. Ok? Colegas, não sei se perceberam. Está a ver o colega Gil Vilanculo a entrar agora. Já estamos a acabar, colega. Então, a informação que eu queria deixar é que enviei-vos um e-mail com a ficha da avaliação para preencherem e retornar a ficha por e-mail para os endereços lá indicados até antes das 13 horas de hoje, até 1 hora da tarde. A última informação é aquela que o Diva já deu. Voltamos a estar juntos a partir do dia 18 de janeiro e vamos continuar com segunda, quarta e sexta. Nosso contacto vai terminar no dia 26 de fevereiro.
Yes, Dr. Lucas, we received 2 emails.
Yes.
Is the same document?
Yeah, exactly the same. One without subject, another one with the subject. Sem assunto, o outro com assunto. Mas é o mesmo.
That's the same document.
Yeah.
Thank you.
Yeah. Okay. Merry Christmas to everyone.
Yeah, Merry Christmas.
Enjoy the festivities and a Happy New Year.
Yes.
2021. Thank you very much for your time this time. A big hug for all of you.
Thank you very much.
Thank you and
Thank you so
Merry
much.
Christmas.
Thank you. Thank you.